Hey guys, and welcome back. Mr. Cole here as we take another look at a video. This time we've done three videos on static forces, and so in this case, let's take a look at like a car being pulled up a hill, a very common question. Let's do this. Let's look at it in terms of what if the car was just being held on the hill. So instead of let's do one part of this problem that let's do one part like the title suggests where the forces are balanced, and then we'll do a second part where they're unbalanced. So let's take a look at this real quick and see what y'all can kind of come up with here. First, let's do a free body diagram, and we'll do it kind of roughly just on the card. Let's say that there is some force, we'll say it's a tension like a cable. Let's say there's some tension just holding the car on the hill. That's all we've got going on. The car's just being held and kept from sliding. All right, so we would have an mg directed straight down, or fg, whatever it is that your teacher likes. There would be an mg at some angle, of course. We would have a 90 degrees to the plane. We would have what's known as a normal force. I about wrote Fn. I don't do that. I always just write lowercase n. Sorry, I'm in a habit. A lot of teachers write Fn, put a little line above it. I'm very happy just to use a lowercase letter n. And we've got a tension directed up the hill. You could see this same problem with a friction. We just haven't talked about friction. So like there could be a car just parked on the hill and ask what friction is keeping it from sliding. The only difference is instead of a T, if it said friction, we would use a mu. In my case, mu n. You might be asked to use a lowercase letter f. But anyway, we're not going to do a friction in this video. So let's do this. Let's just do a free body diagram on this card. So sum of the force is x. Now, usually this car, you would be told the angle of the hill. Well, here's the thing. Let's do a 30-degree angle. If the car is on a 30-degree incline, then this weight is also at a 30-degree angle as well. And if you're looking at that, having a hard time believe it, well, think about it, guys. If you look at this picture, this angle has to be 90 minus theta based on this. Therefore, that's got to be theta on the other side. So that's got to be 30 degrees. So let's take a look at the problem. We've got a T going to the right. And let's do this. Let's draw a separate free body diagram. That one's good. But when you're looking at a problem like this, sometimes maybe you need to look at it with your head tilted a little bit. As in, let's draw it away from that picture and see that we have a tension to the right. We have a normal force at 90 degrees to the surface. And then we have an mg acting at some angle of theta. We'll say that's 30 degrees angle of the hill. So now, that's better. Let's do a sum of the forces based on this picture. And essentially, all I've done is taken this hillside picture and just kind of leveled it out so it's easier for me to look at. So I've got tension to the right minus, I've got an mg, and now we need to look at this. Which component of this mg is directed in an x direction? And so we're using an angle off the y-axis. So I'm going to be looking at this opposite side of this. So T minus mg sine of my angle, and I'm going to set that equal to 0 because this problem said the car is being held. Now, let's go back and let's do a sum of the forces in the y direction. And we've got a normal going straight up in my picture. Normal minus, in this case, mg. And this should be easy, guys. We've already talked about in these videos. If you've got an mg sine 30 in one expression, you've got to have an mg cosine 30 in the other. But now let's make sure that you do understand why it's mg cosine of 30 equal to 0. And that's simply because if you take a look at this picture again, let's do a blue again, the y component, so if this is your y-axis, the y component is, remember cosine of theta is equal to adjacent over hypotenuse. This would be your adjacent component, and so that's why we're using that. So in this problem, it would probably be pretty easy. If it gave you a mass of the car or weight of the car, let's say it's 1,000 Newton car, this t would be 500 at that point. So it'd be a pretty easy problem to solve. Might ask you to find normal force. Usually you don't do a lot with normal force unless friction is involved. And again, if this problem had friction, all I would do is go back to the beginning, and instead of T, I would write mu n for friction up here, or lowercase f, or fk. Ooh, not fk. In this problem, it would be fs, static friction. Now, what would happen though? Let's say in our problem, let's say that this snow is basically frictionless. What would happen if the rope broke? So there was no longer, if there was no friction holding the car on the hill, if there was, ooh, I was going to try and steal my car off this picture, but it would be pretty messy. What if there was no friction or anything acting on that car? Let's just do this real quick. I'm gonna sketch a car. So let's go back. Same hill. So here's a car. Maybe that's more of a pickup truck. And so it was being pulled up the hill. Oh no, the rope has broken, guys. What would happen to this car now? And there is no friction in this problem. Let's look at your diagram. We would have an MG that is straight down. I'm drawing that MG really kind of trying to show you why this idea is that if the hill is at an angle of theta, then if the hill is at an angle of theta, then that means the mg is also at an angle of theta. And here's the thing, guys, if there's nothing going up the hill, then you've got an mg, and then you've got, give me a red again, please, then you've got a normal force acting at 90 degrees on this. And that's it, guys. Two forces. What would the free body look like on this? Let's go back to a black. Let's draw a free body diagram that's kind of laid out here like this. And I'm going to draw these forces. We've got an mg at an angle of theta, and we've got a normal force. And that's it. So if this rope breaks, this object is obviously going to start the direction of our motion. It's going to roll down this hill. Now, since this object is now rolling down the hill, I'm going to make this a positive direction. And so now let's work this problem out. Let's do a sum of the forces x and a sum of the forces y. You've got sum of the forces x. Well, take a look at your picture. In this case, it's going this way, so that's going to be my positive direction. So the only force I have moving in a positive direction is this mg at some angle of theta. And so what I can actually do now is, once again, let's make sure you got this. I'm interested in the horizontal component of that. Well, that would take a sine theta to give me this horizontal component of this angle. I don't want this angle. I want that angle theta I've got defined. So I would have mg sine of theta, and then I'm going to write minus, oh, wait, there's nothing. Guys, that's what tells me something instantly. If there's nothing going against it, then it's definitely an unbalanced force, and the difference is we write ma. Sum of the forces y, on the other hand, we've got an n. I'm still going to call this positive because it's not moving. It's moving in a left to right plane. So that's positive. So I'm going to write n minus mg, and this time it would be a cosine of the angle, and that would be equal to 0. Uh, Guys, hopefully you'll get this, that you will never in like a general physics class have an max and an may. You at least you shouldn't. You should be setting them up where one of them's ma, wherever the motion is, and then the other one's 0. Guys, look at what's beautiful about this. Let's pull that equation down. This is a famous physics equation, because now when you look at it, the problem didn't have to give us the mass of the car. And so what we realize is that for an object sliding down a hill, its acceleration is just g times the sine of the angle. So we could do like 9.8 times sine of 30, so we'd have an acceleration of 4.9 meters per second square. But you are going to see this scenario quite a bit. And like I said, the only difference is, what if there was a friction and it was still sliding? Well, you would have drawn a very short arrow to the right. If it was still sliding down the hill, you'd have a mu in backwards, and we would have had mg sine of theta minus mu in, but we'd still set it equal to ma if it was sliding down this hillside. Anyway, guys, hope this helps you out a little bit. A little long on this video, but anyway, y'all have a great day. Bye.